Okay, so welcome to this video. In this video what we're going to discuss is the phospholipase C beta family of enzymes. Okay, right. Now this is a family of enzymes within a larger family of enzymes known as the phospholipase C enzymes. Okay, and this is the subset of phospholipase C enzymes that are going to be activated by heterotrimeric G proteins. Okay, so generally when people talk about phospholipase C, they most likely mean the phospholipase C beta family of enzymes rather than some of the other phospholipase C enzymes, which are a little bit more niche knowledge. Okay, right. So the first thing to say is that phospholipase C enzymes are often abbreviated to PLC enzymes for short. So P for phospho, L for lipase, and then C for C, so PLC enzymes for short. In addition, they also have another name that sometimes you might see used, which is to call them phosphoinositide specific phospholipase C enzymes. And abbreviated, this is written PI for phosphoinositide, so this means phosphoinositide. The P is for phospho, the I is for inositide. Okay, and then it's phosphoinositide-specific phospholipase C enzymes. Okay, so when people talk about phosphoinositide-specific phospholipase C enzymes, it's just another way of saying phospholipase C enzymes, so it's just a little bit more pernickety. Okay, right, so what we're going to start off with then is talking about the reaction that all phospholipase C enzymes catalyze, which is the breakdown of phosphatidyl inositol 4,5-bisphosphate into diacylglycerol and inositol 1,4,5-trisphosphate. Okay, so we're going to discuss what the structure of phosphatidyl inositol 4,5-bisphosphate is. To do this, we need to discuss the structure of molecules known collectively as phosphoglycerolipids. Okay, so let's begin then with phosphoglycerolipids. Okay, so as the name suggests, these are phospholipids which have glycerol within their structure. Okay, right, so I'd like to start off with the definition of a phospholipid and what you need to satisfy in order to be considered a phospholipid. Okay, and then we'll discuss phosphatidic acid, which is the molecule from which all the other phosphoglycerolipids are derived, basically. They're all based on the structure of phosphatidic acid. Okay, so firstly then, what do you have to satisfy in order to be considered a phospholipid? Okay, so there are two criteria which you have to obey in order to be considered a phospholipid. The first is that you have to have at least one long-chain carboxylic acid within your structure. Okay, so let me give you the archetypal example of a long-chain carboxylic acid molecule. Okay, so the archetypal example of a long-chain carboxylic acid molecule is stearic acid. Okay, and stearic acid is the old name for a molecule that would now be called octadecanoic acid. Okay, and although octadecanoic acid is a somewhat more of a mouthful of a name, it's a more helpful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with an 18-carbon fully saturated carboxylic acid. Okay, so let me draw the carboxylic acid group here. Okay, and now we want another 17 carbons to add on to this carboxylic acid group. Okay, so we're going to have 16 of these carbons in the form of methylene groups. So I'll draw one methylene group, and I don't want to have to draw it another 15 times. So what I'm going to do instead is I'm going to bracket this single methylene group here, like so, and then I'm going to subscript this 16, which basically is going to mean repeat this methylene group 16 times, okay, and then at the end of that, put a methyl group on. Okay, right, and that now is the structure of octadecanoic acid. Okay, so let's just check that we've got 18 carbons. So we've got one here, we've got the 16 in the middle here, and then the final one here taking us up to 18 in total. Okay, so this is an example of a long-chain carboxylic acid molecule, sometimes also known as a fatty acid molecule. Okay, because it is a carboxylic acid molecule, and then its tail is extremely long, so that's why it's called a long-chain carboxylic acid. Now, these long-chain carboxylic acids, they have an extremely hydrophobic tail, okay, and this is one of the basic properties that all lipid molecules obey, okay. So what really is the definition of lipid? Let's just have a look at this. So, a lipid molecule is the scientific term for a fat molecule, okay, and the characteristic feature that you have to have in order to be considered a lipid molecule is you need to be extremely hydrophobic, okay, and what this means is that you do not interact well with water. Now, what properties does a molecular structure need to have in order to make it not interact well with water? Okay, well, it needs to be extremely neutral. The distribution of charge within the molecule has to be such that the molecule is left neutral. Okay, now why does this mean that it can't interact well with water? Well, it's because water molecules are anything but neutral. They have an extremely polar structure. So if I draw a water molecule here, okay, basically water has a negatively charged pole here around the oxygen and a positively charged pole down here around the hydrogens. And the reason for this is that oxygen has a much higher electronegativity than hydrogen, and let me explain what I mean by that. Okay, so in each of these bonds, where we have a bond between an oxygen atom and a hydrogen atom, there are two electrons. Okay, one of the electrons comes from the hydrogen, and the other electron comes from the oxygen. Okay, now, the question is, do these two electrons that are being shared in this covalent bond between the oxygen atom and the hydrogen atom, do they sit directly in the middle between the oxygen atom and the hydrogen atom? Or do they sit towards one side? Well, the answer is they sit towards one side. Now, why? Well, the electrons have a negative charge. Okay, so they are going to be attracted to positively charged things. Now, the nucleus of oxygen and hydrogen atoms are positively charged entities. Okay, so in the nucleus of an atom, you have neutrons and protons. Now, the neutrons are neutral, and the protons are positively charged. So that overall means that the nucleus is a positively charged structure. So these electrons here that are being shared between the oxygen and the hydrogen in this covalent bond, they're going to feel an attraction towards the nucleus of the oxygen atom and also towards the nucleus of the hydrogen atom. Okay, so they're going to be pulled this way by the hydrogen nucleus and pulled this way by the oxygen nucleus. Now the question is, which is going to be a stronger pull? Okay, now to consider that, you don't just have to take into account the pull of the nucleus, you also have to take into account the oxygens that surround, the electrons that surround the nucleus and shield that positive charge from the electrons in this bond here. Okay, so remember, around the nucleus you'll have other electrons, at least in the case of oxygen, not in the case of hydrogen, and these will be shielding the charge of the nucleus from these electrons, and the electrons that orbit the nucleus will have a negative charge. Okay, so to work out which of these pulls is going to be stronger, you have to not only take into account the pull that they will feel towards the nucleus, but also the repulsion they will feel by the electrons that are surrounding the nucleus. Okay, and the fancy word to mean how strong an atom is going to pull the electrons in a covalent bond towards it is the electronegativity of an atom. Okay. So when we say that oxygen has a greater electronegativity than hydrogen, what we mean is that oxygen's ability to pull on these electrons in this covalent bond is greater than the ability of hydrogen. So the electrons overall are going to sit towards the oxygen atom and away from the hydrogen atom. Okay, that overall means that the oxygen will end up partially negatively charged, whilst the hydrogens will end up partially positively charged. Okay, so the water molecule will end up polar with a negative side over here and a positive side over here. Now, this allows water molecules to interact with each other very well. Okay, so if I bring in another water molecule here, what can happen is they can form very strong intermolecular bonds because this hydrogen atom on this water molecule has a partial positive charge. this oxygen atom on this second water molecule is going to have a partial negative charge. In addition, this oxygen atom on this water molecule has a lone pair of electrons here, and this lone pair of electrons is going to form, well, firstly because it's got the partial negative charge of the oxygen anyway, but also because it's a centre of negative charge, it's going to form an electrostatic interaction with the partially positively charged hydrogen here. And this is a strong type of intermolecular bonding known as a hydrogen bond. Okay, right. So water molecules can interact with each other in this very strong way. Now, when you try and dissolve a molecule like stearic acid, octadecanoic acid here, in water, it doesn't work very well because this extremely long tail is extremely neutral, okay? And it's this property that makes it hydrophobic. So basically, this tail consists of carbon atoms bound to other carbon atoms, and then hydrogen atoms which are bound to carbon atoms. Carbon atoms certainly have the same electronegativity as other carbon atoms, so the electrons between, well, the electrons in a covalent bond between two carbon atoms will sit perfectly in the middle and mean that both carbons are neutrally charged. Okay, so you don't have polar bonds there. In addition, carbon and hydrogen roughly have the same electronegativity, so really there's no polarity of the bonds here either, and both of them will be neutral. So this entire structure is neutral, which means that if I was to ram a water molecule against this, the water molecule wouldn't be able to form very strong interactions with the hydrophobic tail of our long-chain carboxylic acid here. So, basically, this is why fat and water do not mix well, because if you try and get the fat to mix with the water, it means that the water is going to have to break bonds with other water molecules to form bonds with the hydrophobic tail of the long-chain carboxylic acid, okay, or the lipid molecule more generally, okay, and basically that's not energetically favourable because you're breaking a strong bond to create a weak bond. Okay, so what will always happen is over time the fat will separate out from the water because it's more favourable for the water molecules all to interact with one another and push the fat into a separate layer, okay, to minimise the contact between fat molecules and water molecules. That's the most energetically favourable solution. So that's why these neutral structures become hydrophobic. But it's not that water actually repels these things, it's that water would just rather be bound to other water molecules than to fat molecules. So the fat molecules all end up aggregated together away from the water molecules so that the water molecules can interact with each other basically. Okay, right. So, that was a deviation to discuss what a long-chain carboxylic acid or a fatty acid is. Okay, so it's one of these carboxylic acids which has a really long neutral or hydrophobic tail, but they're effectively the same property. Okay, right. So you have to have at least one of those within your structure. Okay, so that makes you the lipid portion. That gives you a hydrophobic portion that doesn't interact well with water. Okay, the other criterion that you have to obey, and I'm just going to colour in these two criterions. So here's the first one, here is the second one. The other criterion that you have to have is that you have to also have a phosphate group within your structure. Okay, so let me show you what a phosphate group is. So a phosphate group consists of a phosphorus atom at the centre, double bound to an oxygen atom. And then this phosphorus atom will also have two alcohol groups coming off it, 1, 2. And then finally a single bond to another oxygen atom, and this final oxygen atom here will have acquired an electron via ionic means, and therefore it's left with a negative charge. So this is the structure of phosphate group. So to be a phospholipid you have to have some long-chain carboxylic acid within your structure, and I want to stress this is an example of a long-chain carboxylic acid here. Okay, so stearic acid is an example of a long-chain carboxylic acid, but there are many other examples. So this is a very sort of vague criterion. There are many different molecules that you can have to fill this long-chain carboxylic acid criterion. Okay, right. And then finally, you also need to have this phosphate group. Now, this phosphate group is the complete opposite of the long-chain carboxylic acid portion, because this is extremely polar. In fact, this is better than polar. These water molecules just have partial charges. This has a full ionic charge, so this is better than this. Okay, so this will interact with water molecules stronger than water could interact with other water molecules. So water molecules love to interact with phosphate groups, and that's the key thing that phospholipids have. They have a very, very polar portion that's going to interact with water brilliantly, or a hydrophilic portion, meaning likes water. And then they have a hydrophobic portion which won't interact with water well, and will interact with other hydrophobic molecules well, simply because they'll all aggregate together, because they're being pushed out of the way by other water molecules who want to interact with each other rather than these hydrophobic groups. Okay, right. So now on to phosphoglycerolipids. Okay, so phosphoglycerolipids are a subset of the phospholipids. Okay, there are many different types of phospholipids, but the phosphoglycerolipids are the main subset of phospholipids that are important within biology. There are others, such as the sphingomyelins, but for our purposes, the phosphoglycerolipids are the only ones we need to study. And to be honest, when you think of a phospholipid, you're probably, if you're visualizing a picture in your head, the picture you're thinking of is probably a picture of a phosphoglycerolipid rather than a sphingomyelin. Okay, so let's discuss what a phosphoglycerolipid is. So phosphoglycerolipids are all going to be based on a molecule known as phosphatidic acid. So we'll start with drawing a cartoon of the structure of phosphatidic acid then. Okay, so phosphatidic acid consists of a glycerol molecule as the backbone for the entire structure. Okay, so this vertical line, and I'm only going to draw a cartoon, I'm not going to draw a molecular formula for this. Okay, I think it's easier if we just draw a cartoon. I'll do the molecular bit occasionally. Okay, so this vertical green line is going to represent glycerol. Now, the proper name for glycerol is propane 1,2,3-triol. And although propane 1,2,3-triol is certainly more of a mouthful than glycerol, it's a useful name because it tells you exactly what you're working with. It tells you that you're dealing with a free carbon molecule where you have alcohol groups coming off the first, the second, and the third carbon of that free carbon molecule. Okay, so we're going to let this green line represent that glycerol molecule, and to the first alcohol group that comes off the first carbon of the glycerol molecule, we are going to attach a long chain carboxylic acid. Okay, shown here in orange. Okay, so this horizontal line in orange here will represent a long-chain carboxylic acid, or a fatty acid, and for short I'll abbreviate fatty acid to Fa, that has been linked to the alcohol group that comes off the first carbon of the glycerol molecule via a ester link. Okay, you're going to then do the same for the alcohol group that comes off the second carbon in the middle of the glycerol molecule here. You're going to attach a long-chain carboxylic acid, or a fatty acid, via an ester link. Okay, right, so let me show you, just to remind you what the bond of an ester link looks like. So, if we have our carboxylic acid molecule here, so here's our carboxylic acid group, and I'll just put R here to mean an arbitrary tail there, so this can be whatever you like. Okay, then we'll have the alcohol group that comes off the glycerol molecule. Okay, so in green here, this will go off to the glycerol molecule. Okay, right, so we want to bind the carboxylic acid molecule to this alcohol group that comes off the glycerol molecule. Okay, now to do this, what we're going to do is we're going to remove the alcohol group that comes off the carboxylic acid molecule. We're going to remove the hydrogen that comes off the alcohol group. Okay, we're then going to bind these two structures together to produce water, which is why this esterification reaction is known as a condensation reaction, because it produces water. Okay, and we're then going to bind the carbon of the carboxylic acid group to the oxygen of the alcohol group here. Okay, so that bond between the carboxylic acid group's carbon and the alcohol group's oxygen atom, that's known as an ester link. And the process of forming an ester link like this is known as the esterification reaction. Okay, right. So we are going to esterify two long-chain carboxylic acids to the alcohol groups that come off the first and the second carbons of the glycerol molecule. Okay, right. That's not phosphatidic acid complete yet. Okay, that's just diacylglycerol at the moment. To complete phosphatidic acid, what we need to also do is add something onto the alcohol group that comes off the third carbon. And what we're going to add is a phosphate group. Okay, so in pink, this little blob here, this is going to represent a phosphate group. And I would just like to discuss with you how we're going to attach a phosphate group onto the alcohol group that comes off the third carbon of that glycerol molecule. Okay, right. So this is going to be done by a reaction known as phosphoesterification, and that name should suggest that it has parallels with an esterification reaction. So let's say this is the alcohol group then of the third carbon of the glycerol molecule. Okay, let's say we bring in a phosphate group here. Okay, so remember a phosphate group consists of a phosphorus atom at the center, double bound to an oxygen atom with two alcohol groups coming off it, and then a single bond to an oxygen which has acquired an electron via ionic means and therefore has a negative charge. Now, if you look at this portion of the phosphate group here, which has the phosphorus atom at the center, double bound to an oxygen atom, then with an alcohol group coming off it, that looks incredibly like a carboxylic acid group. In fact, if you replace that phosphorus atom with a carbon atom, ignore the fact that it's got 5 bonds coming off, which is clearly absurd for carbon, but if you just replace that phosphorus with a carbon and look at the portion that I've highlighted in green, that would look exactly like a carboxylic acid group. Okay, and this carboxylic acid-like group that we have within the phosphate group can interact with the alcohol group of the third carbon of the glycerol molecule just like a carboxylic acid group would. So you're going to take the hydrogen off the alcohol group, you're going to take the alcohol group off the phosphate group, you're going to now bind the oxygen atom of the alcohol group to the phosphorus atom of the phosphate group, and this link here that we formed, which is analogous to an ester link, is called a phosphoester link. Okay, so that's how we're going to attach a phosphate group onto the alcohol group that comes off the third carbon of the glycerol molecule. Okay, this structure we've created now, where we've got a glycerol molecule with 3 groups coming off the sides of its 3 alcohol groups, 2 long-chain carboxylic acid molecules coming off the first and the second carbon's alcohol groups, and then a phosphate group that comes off the alcohol group off the third carbon. This is now phosphatidic acid. Okay, right. So the first thing I want to point out is that there is not just one phosphatidic acid molecule, okay? Because I did not tell you which long-chain carboxylic acids to use here. I left it arbitrary. Okay, which means that you can use different long-chain carboxylic acids here. In addition, they don't even have to be the same long-chain carboxylic acid which you use in these two positions. You could use stearic acid here and maybe another long-chain carboxylic acid here, such as palmitic acid, myristic acid, linoleic acid, oleic acid, all of these, you know. There are many, many examples of long-chain carboxylic acids. So you can put 2 different long-chain carboxylic acids here, and of course there are many different ones that you can have in each slot, so that means there are many different phosphatidic acid molecules. So there isn't just one phosphatidic acid molecule, it's really a whole family of different molecules. But they all have the same basic properties because, to be honest, the exact fatty acid which you use here doesn't really make that much difference. All that matters is that it's a really long hydrophobic molecule that you have attached via ester link here. Okay, right. The second thing I want to discuss is the difference between phosphatidic acid and phosphatidate. Okay, so people will often not talk that much about phosphatidic acid, okay, and they'll talk more about phosphatidate. And the reason is that phosphatidic acid usually exists as phosphatidate when it's within the cell, and let me explain what the difference between them is. So basically, phosphatidate is the conjugate base of phosphatidic acid, okay? And just in case you've forgotten what that means, I'll remind you. So basically, phosphatidic acid is an acid because it has this alcohol group here on the phosphate group of the phosphatidic acid molecule. Okay, basically what you'll notice is that even once we have attached this phosphate group to the alcohol group that comes off the third carbon of the glycerol molecule via a phosphoester link, we still have this group that I'm circling in blue. That still exists, basically. You've still got this phosphorus atom double bound to an oxygen atom with an alcohol group coming off. This is still going to be whole in the phosphatidic acid molecule structure. Now, this is also one of these groups which I called a carboxylic acid-like group. Okay, I don't think that's official nomenclature, but that's a useful concept. So it's a very similar structure to a carboxylic acid group, and it can donate its proton off this alcohol group just like a carboxylic acid molecule would. Okay, so what can happen is, at present, we have a covalent bond between this oxygen atom and this hydrogen atom, where you have two electrons within the covalent bond, one from the hydrogen and one from the oxygen. What can happen is the hydrogen nucleus, which just consists of a proton, usually at least, the main isotope of hydrogen only has a single proton within its nucleus and no neutrons. There are, of course, other known isotopes of hydrogen where you have neutrons in the nucleus, but they're less common. Okay, so the main form of hydrogen just has a proton there, okay? So what will happen is the proton will go off and leave the electron with the oxygen atom, okay? So the oxygen atom will therefore gain a negative charge, and you have donated a proton into solution. And that is why phosphatidic acid is an acid molecule, because the definition of an acid molecule is a molecule that is capable of donating a proton away into solution. This molecule that I have described to you is capable of donating a proton away into solution, and therefore it's an acid. So what then is phosphatidate? Well, phosphatidate is the name for the molecule that you have left over after the phosphatidic acid molecule has donated its proton away. So once the phosphatidic acid molecule has lost its proton, the oxygen therefore has a negative charge. The molecule has no more protons to donate away, okay, so it's no longer an acid molecule because it can't donate protons away into solution. Instead, it's actually a base because these two negatively charged oxygens, which are now effectively equivalent, both of them could accept protons out of solution. Protons could come and bind to them, and the definition of a base is a molecule which can accept protons out of solution, okay, so phosphatidate is phosphatidic acid once it has donated its proton away into solution, and it is now a base. And this is a running theme for all acid molecules, that once they donate their protons away, what's left has a negative charge, and that molecule that is left is now not an acid anymore but a base. Okay, so people usually would draw some sort of formula like this. So HA represents the acid molecule with its proton, and this really is an acid. Okay, and then it will donate its proton away into solution, and then the name for this molecule that you've got left over, this is called the conjugate base of the acid, okay, because it's no longer an acid, it can't donate protons away into solution. Instead, it's a base because it can accept a proton back into solution to return back into the acid molecule. Okay, right. So phosphatidate is the name of the molecule where you've donated that proton off that alcohol group, and you've therefore got two oxygens with negative charges on them. Okay, right, now the reason everyone talks about phosphatidate and not phosphatidic acid is that under physiological pH, which is around 7.45, okay, whoops, not like that, 7.45, not 7.55, 7.45, usually what happens is phosphatidic acid molecules have donated their protons away and therefore are phosphatidate molecules. So usually most of the phosphatidic acid molecules within a cell will have donated their protons away and therefore will be phosphatidate molecules. So most people talk about phosphatidate rather than phosphatidic acid, but you know, they're just the two sides of a coin, if you like. Okay, right. So, the reason we have discussed phosphatidic acid is that it is the molecule from which all of the other phosphoglycerolipids are derived. All of the others are modifications of this. Okay, this is considered a phosphoglycerolipid. It's kind of the basis for all the other phosphoglycerolipids. Okay, and all of the other ones are going to come from this. Now, the final thing I want to say in this video is that phosphatidic acid is also a phospholipid because it satisfies our two criteria of having a long-chain carboxylic acid within your structure. It in fact has two, so it certainly satisfies that, and it's also got a phosphate group within its structure, so it satisfies both of the criterion, and therefore you would view it as a phospholipid. Okay, and you do have a little bit of phosphatidic acid, which, as I say, will exist in the deprotonated form phosphatidate within cell membranes. Okay, right, so in the next video what we'll start with is how to modify phosphatidic acid molecules into more general phosphoglycerolipids, and then we'll discuss phosphatidylinositol 4,5-bisphosphate as an example of a phosphoglycerolipid.